In this video, we'll be looking at the 2017 BC question number 6, the Taylor-Maclaurin question. So they give me f of 0 is 0, f prime of 0 is 1, and then they give me a strange recursive function that will help me find the derivative. So they're saying that f of n plus 1 at 0, so the n plus 1 is counting which derivative it is, equals negative n multiplied by the nth derivative at 0. So if I want to find the n plus 1 term, I need the nth term or the one before it to do that. So a little strange, but we'll see what that looks like down the road. So they give me a function f, has all orders from -1 to 1. That's the radius of convergence. Derivatives of the f satisfy the condition above. Maclaurin series for f works for absolute value of x less than 1. So part A shows that the first non-4-0 terms of the Maclaurin for f are x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4. So that's nice. They give us the answer here. We just have to verify or make sure that that actually works. I have to do a little bit of work to find the general term, so we'll see what that looks like. So first thing I want to do is just write out my general polynomial of fourth degree and see what that looks like. So it's P4 of x equals basically all of my derivatives match with the powers, match with the factorials. And so really you need to find your list of derivatives. They're nice. They give you the first two, but then you have to find the next one. So f of 0 is 0, f of 1 is 1. Here's where it gets a little bit tricky. The second derivative at 0, to find the second derivative, really I'm plugging 1 in for the n right here. 1 plus 1 would give me f of 2, or f second derivative. So I'm going to plug on 1 for both of those. That means I want a -1 here, or negative and then a 1, and then the first derivative at 0. So that's where I'm getting this -1 and then this one right here. If I want to keep going and find the third derivative and the fourth derivative, I got to do the same idea. I have to plug in, let's say, a 2 in for this n, and then a 2 here, and then a second, or a 2 here for the second derivative. If I want to find f of 4, I need to plug in a 3 for this n, and a 3 for both of those n's, and that gives me that list of derivatives right here. So we're going to use those numbers, those coefficients, and plug those in for our derivatives. So I'm going to go ahead and plug in a 0, 1, -1, 2, and a -6 in for all my corresponding derivatives. So it should look something like that before I do some simplifying. So the 0 obviously go away. 1x I'll just write as x. Not much I can do with this second term right here. Here I can reduce the 2 and 3 factorial. So 3, that's 3, 2, 1. So the 2 cancels. So basically the factorial and the 2 cancel each other out. This 4 factorial is 4, 3, 2, 1. This is really 3, 2, 1. This 6 right here. So they cancel each other out as well. So the simplified version is what they gave us for part A, which is great. They do say write the general term of this, so I have to do a little bit of pattern recognition here. Looks like I'm going from, x goes from, looks like 1, 2, 3, 4, so it looks like it's x to the n. It is alternating, goes positive, negative, positive, negative. If I start at x equals 1 for this one, I would go -1 to the n plus 1, and then x to the n all over n. So that would be my general term for this one. Of course, you can double check, plug in a 1, make sure you get the first term. Plug in a 4, make sure you get the fourth term there, and it's all matching up pretty good. In part B, they ask us to determine whether the Maclaurin series described in part A converges absolutely, conditionally, or if it does diverge at x equals 1. So let's go ahead and write that in a series and start to think about this by plugging in an x equals 1. So there's my general term in my sigma notation, and then when x equals 1. So we're going to go ahead and plug in a 1 for that x. Well, 1 to the n just goes away, and so really it's just the alternating series of -1 to the n plus 1 all over n. So I'm trying to figure out if that conditionally absolutely converges, or does it diverge. So we're going to check and see what's going on here. It is an alternating series test. So remember, the alternating series, you really just need to check to make sure that the term goes to 0 if I were to take that alternator out. So I'm going to ignore that alternator. Just look at my a sub n part of that, and that is just 1 over n. So if I do the limit as n goes to infinity on 1 over n, that goes to 0. And that means that by the alternating series test, this will converge. The other thing you want to check is, does it absolutely or conditionally converge? And basically that means, did it converge because it was alternating? So if I remove the alternator, if I absolute value that, I'm going to look at the absolute value of that series and see, all right, is that what mattered? And so I'm going to basically remove that part out, which simplifies down to just the series 1 over n, which that's the harmonic series or the p series where the power is 1, and that one does diverge. So the series diverges when it's 1 over n, but the alternator speeds it up just enough that it's going to make it converge. So since one worked and the other didn't, this Maclaurin series will conditionally converge at x equals 1. Conditionally because the alternator is what made it converge. And for part C, they want us to write the first 4 non-zero terms in the general term for the Maclaurin series of g of x equals the integral from 0 to x, f of t dt. So we're going to bring in that polynomial that we found from the beginning, f of x or p of x, and we're going to replace all of it with a t. We are using our x's in our variables for g, so we got to make sure we sub those out. So let's go ahead and just write that in here. So we have g of x equals the integral from 0 to x, and that's basically the thing that I found in the previous part, the polynomial with the general term, and then of course just with respect to t. So all I need to do is antiderive, just do a power rule, and so we're going to power rule each one of those terms, and so g of x would be t squared over 2, t to the third over 6, all the way down the line. This part at the end here is a little bit tricky, but I basically have this t to the n. I'm going to raise that by a power, so that's why it goes to t to the n plus 1. And then it only had an n to begin with, but I have to divide by the new power. So I'm going to raise it by a power and divide by the new power. So that's where that part comes from right there. Then we just plug in the upper minus lower. Upper on this one is an x, so basically all the t's will turn into x's, and then minus 0. So a 0 plugged in for all those t's does just equal 0. So I am going to write the minus 0 at the end here, but you didn't really need to write that part. In part D, they say let p sub n of 1/2 represent the nth degree Taylor polynomial for g, evaluated at 1/2. So g is the function we found in part C, so we just found that. So they say use the alternating series error bound to show that, this is always kind of a mouthful, but it's saying that the actual value using the fourth derivative or the fourth degree polynomial at 1/2 versus the actual function value. The difference between those two is your error, or whatever your approximation is going to be. They want us to show that's less than 1 over 500. So what I think about is, for the approximation, it's as accurate as whatever that first unused term is. So that's the max error off it could be. So we're going to use that first unused term. Well, if they tell us we're using a fourth degree for my approximation, that means that the next term in that that I didn't use would be what I want to use. So that would be the fifth term. So the fifth degree term, that negative x to the fifth over 20, that's the term that I want to use. So if I plug a 1/2 into that, that will be my error, or the max that my error could be. So kind of wordy here, but the difference there, basically saying the error is plug in a 1/2 in for the x on that fifth term. And then we just do a little bit of cleanup there. 1/2 to the fifth is 1 over 32. And then divided by 20, you can move that to the bottom. And so it ends up being 1 over 640, less than 1 over 500. I'm not too worried about the plus or minus. We're absolutely valuing it. So it's just saying that is as the max error that it could be. That's how accurate this one will be.